Hello, and I'm finally back with something. I don't know if it's something that people will be interested in, but my idea was to do some kind of edge details to a Vellum simulation, and I have some reference here from a project I did. This kind of edge details on where it's fractured, and yeah, you see it best in the first shot, I guess. Like these edge details, and they're kind of hard to do. Not very hard, but there's still some kind of you need to do a bit custom things because these are made post-sim, and then there are these a little bit longer things as well, but they're not very visible here. You can see them here somewhere. So we start in Houdini as always, and we start by doing a very basic Vellum sim. Sorry, I'm just gonna bring up my little sheet here. So we start by dropping down a planar patch. Oh, of course, we drop down a geo, and step into it, and drop down a planar patch in order to just give us something. And we do it on the XZ plane, and we can bring up the resolution a bit. You don't need that high resolution for Vellum, but maybe something like this. We have 4,000 points, and we start by just giving it a edge group here. So we're gonna do a group. Of course, we want to have something to get it stuck by, so we just do an edge group where we do unshared edges, so we have the points of our unshared edges, because we want this to have somewhere to attach, but I only want the sides, so I'm going to do another group. We can call this first group edge maybe, and then we do another group, and we also have that over edge and change it to points as well. And we do a bounding box, and we, instead of replace, we're doing subtract, and we just bring this bounding box down a little bit, like this, like that. So there we go. So we just have those points, and then we can put down our edge fracture in order to have this able to be fractured. So we bring up the piece attribute here as to see. And the start is we have some initial pieces, and they're quite uniform distributed, and we don't want to keep them at all, so we just remove them, and instead we do draw curve. Draw curve, and we just plug in the geometry to paint on, and we do the projection on geometry instead. So what we want here is something that goes from the start to the end in order to fracture it completely. So we just start drawing a curve, and start outside, otherwise it will not really work. So we draw it all the way, and hopefully we got something there. Let's plug it into the edge fracture and see. Yeah, so here we have a fracture, and that's good. We will also give it an ID, because we will need that later for the post-sim things. So we just do I at ID is equals to ptnum. So we just have a point number as our ID. And then we do a little bit of attribute noise, because we want to do a noise for our fracture, so it's not completely even. So we can do a float here, and we can call it just threshold or something like that, threshold, or you can do it break threshold scale is the default attribute that we use. And we just do a multiplet. No, we don't, because we need something here. We just do an add, and we can remap it, so we have something that's a little bit lower at some points, then maybe a bit more in the middle and a bit less in the end, just a not normalized distribution. We can remove output raw value, and then the ramp is exactly what we get. If you have output raw value, you will get a more distributed towards the middle thing. So let's see how this looks. Come on. There we go. We need a little bit more of just bring down the element size, so we have something like, I don't know, maybe smaller, maybe like something around that. And that's good, I think. We don't need to post-process this because we don't go below a value anyway, so we can just keep that off. Then we can do a Vellum configure cloth, just to get something. And here we can keep it kind of as it is, maybe bring down we can look at the thickness. I think it's a little bit too thick. It's a very thick cloth right now, I think, so since we're not that high in resolution, we bring it up to maybe 12 instead. And also we might want to bring down the bend stiffness a bit, maybe to 0, a few more zeros in like 5 zeros before that, I think. I think that's good. And we could also bring up the damping ratio a little bit, and we can bring up the damping ratio for the stretch a lot more, because it, in my opinion, when you do braking, it tends to get kind of jittery. So bringing up the damping ratio helps. We could maybe even bring it up further, I don't know, but let's try that. And we bring down the rest length a little bit to get it a bit more tense, I would say. And then we can bring down another Vellum constraint, and we can do like that, and we can do weld points. And we can do calculate varying on these as well, so we have some kind of thickness to it. And that's all good. We have something here. Then we want something to break this. So we drop down a tube, and let's just change it so we can bring it down a little bit. Minus 0.1 maybe, and bring down the radius to 0.1. And I think this is good. We can do it as polygons. You could bring up the resolution if you want, it doesn't really matter. Then we do a transform here. Then it crashes, of course. Yes, let's bring it up. Sorry for that. And that reminds me that I should save this as well. So let's just save this. I'm just gonna save it. Sorry. Now you see everything I got here, which isn't that secret, so it doesn't really matter. Just gonna call this Vellum edge. Great. So we have our transform here on the tube, and what we could do is we can do a pivot, so we translate it to y min. So we just bring the pivot down to our bottom here, and then we can do a rotate minus 90 degree plus $frame maybe. So what we have now is this, and I think that's good. And let's just see here, it goes just where our weld is, so that's good. Then we can drop down a dopnet, and we plug the first, the geometry in the first, the constraints in the second, and the collisions in the third one. And here we need a Vellum object. You could just do a Vellum stop solver as well, I guess. And the Vellum object default has input 1 and 2. I'm just going to copy this, bring down a static object, and just do the stop path, and change this to a 2, and use the form geometry. And then we do a Vellum solver. We bring in our object, we bring it down here, and we bring in our gravity as well. And I just realized I forgot to pin the points, so let's do that as well. So go up to our cloth, and we have pin points. We can do the edge, and we can do pin type and permanent, and then we get this. So that's good. As you see, we get very, very much like this, and that's because of the substeps mostly. So we can then do a merge here in order to merge in our collision geometry, and I'm going to do mutual here because eventually we will need more things. and it works. I should add end caps to this as well. It doesn't break anything or so, but that's fine. So I'm gonna add end caps here for reasons that will be apparent later. So let's see this now. It just flaps. The thing is that it doesn't have enough constraints in order to not make it the stretch constraints doesn't have enough to work with. So what we need to do is bring up the substeps to at least 5. We can start with 5 or maybe come up to 10 immediately. And what we see then is that we have something that's a lot more controlled. The thing is with substeps that when you do these kind of things with stretch, you need quite a lot of them in order to get the cloth not stretching. And also the break is also dependent on the number of substeps. So if you change substeps, you also will need to change the break value. So let's look at the break value now. So we have on the weld, we have braking. So we can enable that. And we can bring it up to 0.2. And we can scale by our attribute, which we just call, what do we call it, thresh. So there we go, now we have something like that, and if we run this, we will start to see something that works a little bit. We can bring it down to 5 substeps maybe just to see a little bit quicker. It will change the break value, but let's see, just to see something. You see it goes down a bit more. It's very floppy still. We could also add a little bit of velocity damping in the solver. Let's see if it breaks here. It breaks quite late, but it breaks. So there we go. Seems to be working. Quite nice. Yes, it works. It actually solves it quite well with this. We have some problems here. Yes. You see here we have intersections and stuff, which is not very fun. The reason for that, I think, is that we have layers of cloth here. It gets layered, and it doesn't have enough info to solve it. What we could do then is just bring up the post-collision passes to around the number of layers we have. So we might get up to 6 layers here. I'm not sure, like 1, 2, 3, 4, maybe 6. So to be safe, we bring it up to 6, and hopefully that will solve a bit of a problem. And also bring up the substeps will of course also help. So when we bring it up to 10, it will probably help as well. Still a bit buggy here. So I think with 10, with this and with more substeps, it will work. One thing we also could do, we don't get that much problem intersections, but if we were to get intersections here, which is not uncommon when you do braking and big stiffness, is that we could also add a VDB collider, which would help if we would have intersections. So we can do that just to have it so you know how to do it. It's quite simple. So the default here on the collisions is use solver default, and for Vellum that is the surface. So that's what you're using right now. But we could also do one version where we have volume collisions, And if we bring up that collision guide and plug it in, we don't see anything. Let's go back to start, and there we see it. So I think this low res will work good enough. It's quite low res. Could give it a little bit more, but I don't think it's. Bring it up to 50. Give it a little bit better representation, something like that. And having both of these usually helps if you have fast moving geometry and stuff. Not sure if it's needed now, but it could help us a little bit. So I'm just gonna bring up the substeps to 10 and cache a little bit, and I'll see you in a second. And here we go, we have something. Just look at how it looks. It's very jittery still, but we seem to have fixed most of the problems. We have a little bit of a problem there, but we don't care about that at the moment, I think. So this is good. In order to fix the jittering, we're just going to bring up our velocity damping to 0.15 or something. And I'm going to cache this and see how it looks. So what we need to do is to do two DOP IOs. And we're just going to bring in our DOP network. And we're going to do the felt object vel, because we just want the Vellum object, not the collision geometry. And we're going to import the geometry. So there we go with that. We do a copy of this, and we do constraint geometry. And then we can do a Vellum IO in order to cache both of them. And we don't care about our collisions. So I can bring this down to maybe 120 frames or something. And I'm just gonna cache this. Good, and we have this, which is cool. It's not the best sim, but that's not the point here. So now we need a Vellum post process. And here comes the bit tricky part in order to add these details. There are probably better ways to doing this, but this is the way I've done it, and it works at least. Although it kind of it's kind of a bit of a hassle. So I'm going to subdivide this to something that I want in the end, maybe 2 subdivisions. I don't know if it's needed. And the first thing I'm gonna do is I'm gonna start by getting the curves here. So on the post processes we have a default value of apply welds. We don't want to do that, which gives us this little cracker here, because you can't really see it. You see here that we have this line here that's not very nice, but we will need it. So we're going to drop down and wrangle in order to give it IDs, because we will do a fuse later, so we will need to have the original point number. So I'm just going to do I at ID equals ptnum in order to store that. And then we're going to drop down a fuse in order to fuse these. So we could also drop down and apply welds, but it doesn't really matter. And then we're going to do a group, and we're going to do a group over edges, and we're going to just keep it on unshared edges. So we get this, the whole big thing here. And then we also need to know what's the outer edges here, because we just want the inner edges. So from the point wrangle, we just down a time shift, and we put this one on frame 1. So we have the start here. Then we fuse this as well in order to get rid of the edge thing. And then we do another group, and we call this one, we could call the first group here all edges or something. And then we call this group over edges as well, we call it outer. We do the same thing here, include by unshared edges. So now I have these two. And what we could do then is in order to attribute copy this, because we don't have the same, we have 67,699 here, and we have 67,828. So we don't have the same amount of point numbers, and that's our big problem here when we weld it. And when the welds, when when it gets torn, it loses some. It changes point number. So what we could do then is, if we do copy, it doesn't work because we don't have the same point number. So what we do instead is attribute copy. So we just do a wrangle here, and we call on points, we do f at outer equals to 1, and then we do that over the group outer. And then here we can do an attribute copy, and the composite, but copy. And we bring this one in the second input, and we don't want to copy CD, but we want to copy outer. And we want to match it by ID, because we have that. So what we get then is we do color here, run from attribute, outer, we get, let me see here, I don't see anything. Yeah, I see it, you see here, we have this white on the outer edges. So that's good. We could then just form a group from this. We can put down another angle, and we can do if at outer is over 0.5, then we just do a group outer equals to 1. So we create a group from those, and then we promote that to edges. So we do group promote, and we do outer here, and we promote it to edges, and we get a little bit more than we want. So if we do include all the elements at the boundary, we just get the outer edges here, but not the inner, which is good. We can then combine these two groups with a group combine. So we do a group name called combo or something, and it equals to, let me see what it's called. It's called all edges, and it subtracts the outer. And then we just have these, which is what we want. So now we have an edge group here. And that's good. What we want now is points on this one. And we want the points to have a constant point count, because now this group we could convert it just to an edge group, or to a curve, but then we would not have constant point count. So what I do is I just do a time shift again, and this time we just do it, rather than that, we just do it to the end. So we do fend here, and then we have the end where we have all our stuff. And then we could just take the combo group that we have here and do a group promote on that as well, in order to get the primitives here, because we want to scatter on them. You can't scatter on edge group. So we take our combo and we promote it to primitives. And there we go, we have something like that, which is good. We can then do a scatter, and we just do it on our combo group, and we bring up the scatter to a lot, maybe 200k. And we could also bring up the acceleration scale to 2, to get it more evenly distributed. And we could also try to bring up this to 20. I don't think it does matter that much. I don't know, maybe. This is just a one-time operation, so it doesn't really matter. What we also want to do on the scatter is we want to put out the source prim and the source prim UV. So we do that. And then we could do an attribute interpolate. and we take our, we can bring up, go up all the way here and bring that one in. And what we have now is this. So we have a deforming points with a constant point count, which is important here. We could then also give this an ID. So we put on a wrangle and we do I at ID equals to ptnum. That's good. And then we could bring down our combo group, which is this one. And from this one, we could do an labs edge group to curve. And what we get then is, if we take the combo group here again, we get just the outlines here. And if we then, we don't have that many points now, we have quite a few points, but we want it higher. We need this to be quite high res. And this is not the fastest way of doing it, I guess, but if you have a better way of doing it, I'm happy to hear it. But this works at least, so I'm happy with that. So we bring down the resample to something like 0.1. So we have, it's not that many points because it's not a link, so we have 16,000 points. And what we can do then is we could, after this wrangle, we could then do another wrangle in order to see which points are close to the edge, because we have this edge here and we have this point. You see they go in all the way to the primitive. We don't want that. So instead we want to do just want to check the ones that are nearest. I don't know, maybe you could somehow make a curve out of it and scatter instead. I'm not sure. You probably could do this more efficiently. If you do... No, but we won't interpolate. Ah, never mind. We do it this way. It's good to have the primitives because we get a good attribute interpolate. So what we do here is we bring up some variables. We call it near point, which is the near point on the curve. So we just say near point, and we say 1 and at p, so it looks as the nearest point on the second input. And then we do a position for that. So we call it vector position, and we say point from input, the second input, and we look for the position attribute, and we look at near pt, which is the near point we found. And then we do a distance of those. So we say float distance equals to distance at p, our given position, and the position we found on the point. And then we can just do a simple statement and say if distance is greater than our threshold. So we do a channel float threshold, and if that's true, then we just remove point first input and at ptnum. And we could also do a p-scale here, so we can do a p-scale equals to random of the ID. So we have that as well. And why do we get an error here? Is it because we add the I there? No? What the fuck? P-scale. That should work. I've done that a million times. It works now. I probably did some spelling error or something. So that's good. What we have now is the ability to bring this up to something very small. Maybe like that. And now we have a nice even distribution of points here with the correct ID and everything. So that's good. But now we also want these to orient with our Vellum. So what we can do is we can go back to our Vellum post process and do another stream here. And we can start by adding normals to it. And after that, we just go in and we could do this on points. We could also do an attribute promote. Doesn't really matter if we do it this way or another way. So we just make sure that the normals are on the points. And what we do then is we do an group again. Same procedure as always. So we do a group, and we just do over edges, and we do unshared edges. If we remove this, we have this, and then we can do an edge group to curve. And we just do our group 6 here, and we have this, which is good. We then don't run a polyframe in order to compute things here. We also want to compute the tangent V. And then we can run a point VOP in order to calculate the orient. You could do a orient along curve, but I found it to be a bit less precise here. So in the point VOP, we're just gonna do some things. If you look at the normal now, we see that it's not going downwards, so it's fine. Good. Or is it? No, it's fine. So what we do is we want to bind in our tangent and our bitangent, etc. Tangent U, tangent V. So we just do a bind, and we bind in tangent U. You can just plug it into normal to see what we get. It's hard to tell here. I don't know if it's shown. Oh, because it's a float. Sorry, there we go. We have a tangent U, it works. And we bring in a tangent V as well. You see that that works as well. It does. And then we have our normal. We can just use that one. So what we want is that we want our normal negated. So we negate that. And then we do a vector to matrix. And we start with our tangent U, then we take a tangent V, and then we take our negated normal. And that matrix is then converted to a quaternion. So we do a matrix to quaternion. And what we do then is a bind export. And we bind this as orient. We can do. Do you have a special? No, we just have for float. It doesn't matter. I think it takes it automatically. So if we remove that and we do an marker for orient. And we do that as an axis, we see something like this, which looks like chaos. We could also just take down the scale and we see something like this, which is good. What we could do now is we can sit down here and we can do an attribute transfer. And we bring in our orient. Orient, there we go. So we have our orient, which is good. What we'd want to do now is we want to have some lines to this. I can remove the visualization here. So it's going to drop down a line. I'm going to give it maybe 10 points and a length of 0.01. And I also want this to be in the middle. So what I'm going to do is I'm going to copy the length here, paste relative reference, and I'm going to copy the direction and do that multiply by our direction. And then I'm going to divide this by 2 and I'm going to do this negative. And what this gives us is this, a line that's centered on Origo. What I want to give this as well, just for shading, is I want to give it a U value, so you could resample it and have it automatically down there. If you do resample, you can do compute a curve U here, but I don't want to do that, so I'm going to apply a wrangle and do it the old school way. We just do f at u equals to float point number at ptnum divided by float the number of points, num_pt, minus 1. And that gives us a u value. If you check the spreadsheet, we see a u value from 0 to 1, which is good. So what we can do now is we can do a copy to points with this. So write down a copy to points, and we bring in our thing here, and what we get now is this. And it looks a bit off. Let's see. Maybe it's off. Just gonna merge this and see if we have something wrong with the orient here. So just bring a Vellum post process and merge it and see here. No, it looks good. And from what the thing is, the inside things could be used if you wanted to. We did on our thing. The look dev people thought it was good to have, so they could do something with, you know, it going a bit inside as well. But that's up to you, of course. What we want now is we want to animate this as well. Now it follows the curve, it follows the direction and everything, and that's nice. It's really nice, but it's kind of static at the moment. So we want some kind of animation, but we just want on the outer part. And the thing is that the U value won't work because it's flipped on some places. You could probably fix that if you're smarter than me, but I do another solution to it, which might be not as elegant, but yeah, it doesn't really matter. So what we want to do is we want to do an attribute transfer. So I'm just going to bring down from the group combo here. I'm going to do another stream. So I'm going to promote this group. So we're going to do group promote in order to just we're going to do the combo, and we're going to promote it to primitives. So we get these, and these are a little bit too small, so we're going to do a group expand. Nice new node, and we can just take a brace group combo, group combo. There we go. So just expand it one area. And what we can do now is just give this, we can just blast off everything else. So we're just gonna blast off everything but the group expand. Delete non-selected, so we have this, and then we're gonna give it a wrangle, and it's gonna give it a call it f at inner equals 1. So we have something here, and then we could also subdivide this because we want to have an attribute transfer that's quite detailed. So I'm gonna give this 3 subdivisions. We have 86,000 points. That's okay. You see here it's quite high res at the moment. And what we could do then is we could remove this merge here, and we can just do an attribute transfer here. And it was called inner right. So we're just going to take the subdivider in second input, and here we're just going to do points, and we're going to take inner. So we're going to attribute transfer, and then we can do a little bit of attribute blur here if we want to. And we're going to blur not P but inner. And we can maybe bring it up to 20 or something, quite a few steps. We can drop down a point swap in order to look at this. Not in order to look at it, but in order to do the animation and things. So here we can bind in the inner attribute. Just plug it into CD to look at it. And we don't see anything. Because maybe we forgot to take down the conditions here on the attribute transfer, of course. Sorry. So we're just gonna bring this down quite far. So we're going down to 0.007. I don't know. Let's see. Here we go. Here we have this. And in order to attribute blur to work, we need to remove the pin border points. And maybe it was a bit too much. Maybe we can take down the step size. That's better, I think. And we could also plug this into a ramp in order to set what we want. So we don't want a color ramp, we want a spline ramp. And now we can control this a little bit more. So this is where we want to apply animation. So maybe we want it something like that. I don't know. It's a bit more points on the shorter ones, or they're more tight, so it gets a little bit random. But that's fine, I think. I think that randomness doesn't really hurt us. So what we can do now is we can bring in an AA noise. And this AA noise we want to animate, so we drop down a position and do a vector to vector 4. And in the fourth input we use time, but we multiply it with a small amount. Could of course divide it as well, but multiplication is a tiny bit faster. I don't think it matters at all at this point. Not the slightest gray, but I've tried to use multiply instead of divide when I can choose. So we plug that into the AA noise. And then we want 3D noise, and we want a higher frequency, maybe around 100. And this noise can then be multiplied with our inner, but we probably want to complement this in order to have it the other way around. So we plug that one in, and then we can do a constant as well in order to control how much this gets us. So we bring this down to 0.1 maybe. Maybe that's way too much, but let's try. And then we can add the whole thing to the position. So we take this product here and we add it in, and we get this. So it's way off. So bring down the constant here to 0.1. And there we go. There we have something that's a little bit better. And we can then tweak the ramp in order to have it less applied. Maybe it's a bit too strong still. We could maybe do something like this. It's a complement, so it's kind of we're just gonna look at this in the merge and see how it looks. So let's bring down this one. Is it the wrong way? No, it's the right way. So here we can see if we bring this one up, we can see where we want the transition to be. And we could of course maybe subdivide this before to get a little bit more. I mean, that's depending on what resolution you want, but we get a little bit smoother result. Or we could also subdivide it before the point VOP in order to get a little bit more detail. And then we could also do a smooth afterwards, just on the position. And see how big you want that. So that's pretty nice, I think. And it works quite well. And then we could also, for our regular Vellum, we could then do another post process instead, where we actually extrude this as well. And I think the extrusion is too big now, definitely. So we bring this down to 0.2 maybe, something like that. I'm not sure. And we just merge it in instead of the other one. And to this one we might also want to apply the welds. And we get a little bit error here, I think. Yeah, you see, we get this thing. And you could take this away as well, but I don't think it's very necessary. I think it looks like when you see it, it kind of adds things because you see that something's happening there where it's about to break. So, but it's very easy to remove. I mean, you can just group it in and remove it with the welded geo. So that's pretty much it. We can look, maybe do a play blast here or something, see how it looks. We could also bring in our collision geometry to see a little bit more. So let's look at it from underneath. I think it's better here. And then you of course have to look at animation as well and see how fast you want it. But I'm just going to do a play blast of this and I get right back to you. Here we can see something at least. You see we have nice details here. And it works quite well. Good. And we can see it here as well, yeah. And so one thing you could do if you get this if you feel it's too jagged, we can just take down subdivisions here to 0 and see what happens. If we want to control it a little bit better and have a little bit less of the the small jittering things. Or you could of course go in and do a little bit spatial blur, and you could also bottom damping and so. But you could also do a filtering post sim. So if we just going to show you that, I'm not going to put it into the rest of the system, but you could drop down null and call it something like out to shops, and then you can do shop network, in which we could drop in geometry, and we could just do auto shops, and we can do it animated. And what we see here is we have the geo inside here. It looks a bit weird. I wonder if it helps if we add normals here. I'm just gonna do very smooth normals, see if that looks, yeah, it looks a little bit easier to see then. So what you could do here is you could do a filtering, and what you get is, let's see here, let's remove this. You get a lot smoother result. We could look at animation, look at motion effects view as well if we want to see what it's kind of hard to tell here, but so much so it's hard to see what's going on. Oh, it's kind of too much information. But if we just bring this up down to 0, maybe we need to go and do a channel here as well. We put down a channel so we can see it here. Take down a channel and we bring in the shop and do it animated. I don't know if there's something happening now. It's in 0. Bring it up to 1. And you can see what's happening. We get a lot smoother. It's way too, it looks like underwater almost now. You see it's super smooth, which might be something you want, but you could also bring down the effect to maybe 0.2 or something, and you get a little bit smoother result if you want that. So that's also an option, and you could also bring down the filter width to maybe 0.5. You get some smoothness, but you lose some of the eccentric, like the motion. It gets a little bit smoothed out. So that's an option as well to do if you want to. The problem is that it's kind of can't handle that much geo, so yeah, you could probably subdivide it afterwards instead of before you do the filtering, in order to get a good result. So yeah, that's it. And then we have the final result, which we looked at, and can just look at this once again. See the effect here as rendered. So yeah, that's the effect. Pretty much the same setup as we did here. Cool, and yeah, that's it. Thank you.